It's H plus and OH that we are using to balance. Okay, so to balance the oxygen part, what do we use? Where will you add OH water to? You add OH to where OH, the oxygen is, to the part which doesn't have oxygen. So it means this must go to that side. Okay, how many oxygens do we have here? 7. Okay, so that means if you make it 7, it's try and error method to see whether it will go. Okay, so let's see. That will mean put this thing here. So you will have O72 minus going to 2 plus 7H2O. Okay, but let's see what happens when you put 7 there. Now oxygen has been balanced, but by putting 7H2O there, what happens? You have added hydrogen to that side, but there's no hydrogen here, so you have to add H plus on this side. How many hydrogens should we add? This is 14, so it should be 14 H plus C out to 2 minus going to 2 C out 3 plus 7 H2O. Okay, so at this point our hydrogen is balanced, chromium is balanced, oxygen is balanced. But the next thing we have to balance is we have to balance the charges too. Let's make sure the charges are balanced. Let's see. Total charge here, this plus 14, this minus 2. So the total charge here is what? It's going to give us what? Plus 14 minus 2 is going to be plus 12. Let's see. Total charge here, 2 times 3, that is plus 6. Okay, plus 6. Right. So 12 and 6, how can we balance them? Unless we are using electrons to balance. So if we add electrons here, it will not come to 12. If we add electrons here, we can get 6. Then it will. So it means you have to add how many electrons here? 6 electrons. Then it will make it 6 here. This will make here positive 6, here positive 6. So we should add 6 electrons there. Alright, so we're going to add 6 electrons. So at the end we're going to have 14 H plus 1, 2, 6 electrons, 1, 2, 2, 7, 8, 2. Okay, so it's balanced now. So this is the equation 2. So equation 1 is here, and equation 2 is there. Okay, so this is what you have. So you have the 2 equations. So what you do is, let me just clean this part so that you can put them together. You have to put the 2 together so that it becomes a redox reaction we're talking about. So add this part to this, and then add that part to that. But before we do that, let's ensure that this is fully charged, this is fully charged. Let's ensure that the electrons that we are going to cancel will be equal on both sides. So you see that here, the electrons should not appear in the final equation. So here we have 2 electrons here 6 electrons. Okay, so let's make sure, and this is on that side, this is on that side. We want the electrons to cancel from the equation, because usually when we are writing equation, don't bring the electrons. So to get the electrons out, also when you are putting them together, make sure the electrons can cancel. This is 2 electrons, this is 6 electrons. How can I make this side 6? You have to make this side 6 electrons so that they will cancel. To make this side 6, this is 2. To make it 6, you have to multiply by 3. So this becomes 3 H2S, 3S, so that has 6 plus what? This is going to be 3, so that's going to be 6 H plus. Okay? Right. That is going to be 2. So our equation, let's say 3. Okay? So when we have done that, now at least we are sure of what we have done, so we can now put the 2 together. Okay, so we're putting them together. We're going to have what? 3 H2S plus 14 H plus chromate 2 O 7 2 minus plus our 6E going to 3S plus 6E plus 6H2 plus, this is going to give us what? Plus 2 chromium 3 plus 7H2O. Right. So this is what you have. Okay? That's putting them together. This is what you have. Putting them together. This is what you have. Okay? Putting this and that together. This is what you have. So when you are done, you can now simplify the equation. That means make sure those which you cancel. So this is on both sides the same thing. If you send it to go and cancel it, it will be 6 minus 6. So this will cancel out this. Now we have 14 of hydrogens here. How many? 6 here. So if you balance out, what do you think? 6 will, if you bring this one here, hydrogens on that side, it will become minus, and then this will become what? We'll have 8 hydrogen minus here. So the final answer will be this. Going into 3s plus 6H plus 2 plus 7H2O. Right. So if you look at it from here, right, so if you look at it from here, you see that we have 8 now. This, that, of course, we have our 6 is out. We have cancelled it, so the 6H is cancelled. It will come here. It has been sent across, so it's no more. So we're going to have that. 3s plus 6H plus 2c. So H6 is not coming. How am I putting 6 there? 2Cr 3 plus 7H2O. Okay? So this will be the balance equation. This will be the balance equation. 3H2S plus 8H plus Cr2O7 Okay, so this is the final answer. Okay? This is the final answer. That is the final answer. Alright. So that will bring us to the end. Alright. So let's look at the last example. That one, I'm going to do it in the base, in the alkaline medium. Okay, so that at least we have gone through that. So the first one, it wasn't in acid or base. Then we came to an acid. We are going to a basic one. Then that will end this section. So let's see this. If this is the question given to us, and then we are asked to solve this one. Okay, this ion reacting with potassium manganate. Potassium permanganate. Okay, so we are doing this in an alkaline medium. So we are doing it in H minus. So we are going to, in that case, we are going to use OH minus, and then water to do the balancing for oxygen. So the same principle. Look at where the first half of the reaction, so this going to that. So that will be Fe going to what? Fe 3 plus, these 2 plus. So look at it. 2 plus becoming 3 plus. It means it has lost electron. If you lose electron, you become more positive. So the loss of electron is here. So this reaction is losing electron. It's not being reduced. It is rather releasing electron and then increasing in charge. So this kind of reaction is the oxidation part. Okay. First of all, we have to balance the atoms. Fe1, Fe2 is balanced. Then we come to balancing the electrons or charge. Here is 2 plus. Here is what? 3 what? Plus. So where are we going to add electrons to balance it? In balancing the charge, we will use our electrons. Okay. So here, electrons. If you put the electrons here, it will reduce 2 to 1 and so on. It will never get to 3. But if you put the electrons, it can reduce this to 2 plus, so that if you put 1 electron, it will reduce this to 2 plus, so that it will balance. So it is better to put the electron here. So here will become what? Fe 3 plus how many electrons to make it charge? It will be 1 electron. Okay? We don't have oxygen here for us to add OH or H2O. There's no oxygen. So So there's the first equation. Let's go to the second one. Manganese, okay? The manganese is Mn. Because this one released is likely is going to accept, okay? So we're going to have this Mn2 plus. Let's see. We should find the charge of M here, Mn here, manganese, okay? So manganese, let's see the charge. Oxygen is minus 2. Okay, so minus 2 times 4 is total is what? Let's put this one here. Total will be minus 8. So, and this one is what? 1. Okay, what should we add minus 8 to get minus 1? Unless this one is plus 7. Okay, so if this is plus 7, we'll get minus 1 for the total. The total is minus 1. So if on the oxygen side the one is minus 8, this might be minus 7, so that it will get minus 1. Okay, so it means here is minus 7. Okay, so it is from minus 7 to plus 2. So to move from 7 to plus 2, you should have added electrons. If you are adding electrons, we're using it to, so it means electrons were added in. Okay, and that is what I said. But we should first balance the atoms first. Now let's see. Manganese is 1 here, manganese is 1. Okay, oxygen is how many here? 4. We don't have oxygen here. So we have to use OH and H2 to balance the oxygen. OH and H2, which one has higher proportion of oxygen? You see that this has higher proportion of oxygen. Because this is just 1 oxygen to H. But here is 1 oxygen to 2. It means the oxygen content here is rather lower with respect to H. So the higher oxygen content should go to where there is no oxygen. And then the lower oxygen content should go to where there is less oxygen. So here, oxygen is more here. This OH is more oxygen. So I'll put it here. I'll put OH here. If I put OH here, how many oxygen atoms are here? 4. So we'll have to put 4 here. If I put 4 here, that will make oxygen balance. Now by putting 4 here, what happens? Oxygen is balanced anyway, but I've added hydrogen. So I must balance it with what? The water part on this side. How many hydrogens have I added? Let's check. How many? 4, right? So it means I must add 2 moles of what? H2O. But let's see what happens. When you do that, now calculate the number of oxygen here. The total number of what do you call it? Oxygen that you have. Oxygen and now will increase to what? 6, because this has been added. This 2 going to make it 6. And here is 4. So how do you go about it? That is where you have to look at this method. Right, so that is it. Let's see. So this is 4 and this is 2. But just watch something. You realize that the more you try to use you are using OH to balance. Always when you do that, this is now making this oxygen 6 here, and this is 4. So you see that it will keep on altering. It means every one step that you take, you have to add another water to it. So it means by the trial and error method, you are not better off starting off with the OH. So what you can do is you can then use your water, which has oxygen, to balance for the oxygen first, and let's see how that will go. Right? So after going through this, you realize that it will be better for you to start with the H plus H2O. Although you have noted OH must come on this side, but it's better off starting with H2O, so that the oxygen will balance for the oxygen on this side. Okay, and then you can bring your OH in. So in essence, what I'm trying to say is if this has oxygen, this also has 1 oxygen. Okay, right. Now both have oxygen, and then this has 2 hydrogen atoms. This has what? H plus. Okay. Now the next thing is if you start with water, let's see how it will be. Now we have 4 here. To get water to make it to balance for oxygen, we can put 4 H2O here. Now when you put 4 H2O, you are balanced for the oxygen. But remember, hydrogen has also been changed. So you should balance for hydrogen. To balance for hydrogen, what do you use? You use the one with the higher hydrogen content, which is this one, water. So that must be here. How many hydrogen atoms are there? 8. So we must put 8 H2O here. Now if you put H2O here, you have also altered the oxygen again. Okay? And to balance for oxygen, what do you use to balance for the oxygen now? You use your one with the higher OH. higher O, which is the OH. So you must use OH to balance on that side. So let's see how it will go. Here we have how many O? 8 here now. Okay? This 4 is balancing. So we have 8 O, which has been added. That means we should have what? 8 OH. If you have 8 OH, let's see whether it will balance. And then the H plus is 8 now. Let's see whether it will balance. This will be what? Our 8. That's 8 times 2, which is what? 16. Okay? And this is 8H. This is also going to be 16, so the H is balanced. And this gives us a balanced equation. Okay, so when you come to the basic medium, what you can do is, since both of them have oxygen, they can balance for oxygen. Okay, right. But you are better off starting with the one, the water component, because the water can also provide you with the OH that you want. Okay, so that as you make adjustments, so you can try as a dry element. If you put the OH there, you see that anytime you want to balance, you have to go forward. You will not be getting anywhere. So it means the other way should work. Then you start with OH. You start with OH, you realize that you're able to balance just after some few steps. Okay. Therefore, that will lead you to come to the conclusion that it will be better for the basic medium to start with OH, using OH to balance for the oxygen deficits. Okay, and then along the line adjust with your HOH minus. Okay, here's the H2O. To start with the H2O first and balance with your OH minus. Okay, so this becomes equation 2. Our equation 1 is here. So between these two, we put them together. But before we put them together, we said we must balance this one. We have balanced the charge. Let's balance the charges for this one. What is the total charge here? This is minus 1. This 0. Okay, so it's minus 1 here. This plus 2. And then we have what? This is minus 8. Okay? So plus 2 minus 8. Let's see what happens. That is going to give us minus 6. Okay? So how many? Here is minus 1. Here is minus 6. What can we do to balance the equation? We have to add. We are going to balance charges, so we use electrons. If you add electrons here, it will never get to 1. If you add electrons here, we'll get to negative. So we have to add plus 5 electrons here. Right, so that will mean the equation will come to this. So the point is, you get to know OH will go on this side because it has more oxygen. Right, that's very nice. But if you start with it, you are not getting, use oxygen, H2O to start and see. So when you start a few steps by adding for OH, you see it will balance out. So this is going to be MnO4 minus plus H, so that you don't need to memorize things. Plus OH plus what? 5e electrons is going to N2 plus 4H2O plus what? 8OH minus. Okay? Now look at this. We are now going to put the two equations together. Okay? This has 1 electron. This has 5 electrons. So to balance, we must multiply this equation by 5. Okay, so put 5 here, 5 here, 5 there. Okay? Therefore, the final answer is going to be 5F2 plus what? NO4 minus plus H2O plus 5 electrons going into 5F2 plus 5 electrons plus N2 plus 4H2O plus 8OH minus. Okay, so the electrons are the same, so they will cancel. Remember, we have water here, 4H2O, so that will also come here. It will cancel 8 water to make it 4. So the final answer will then be what? Let me put it here. So the final answer is then going to be here 5F2 2 plus NNO4 minus plus 4H2O going to 5F2 3 plus NN2 plus 4H2O plus H0, this HO, OH minus plus 8OH minus. Alright, so I think we have looked through. Let's check everything is there. 5M becomes 4, water becomes 4 because 4 has crossed. Electrons cancelling out. Fe5, Mn, that's 4. H2 will not come. Okay, then we have what? 8OH minus. So this becomes the final answer. Alright, so when you're doing it, be more vigilant, and then make sure you capture everything. Note your figures, note your charges. Right. Alright, so at this point, let's look at something small, solubility, some small guide, so that when you are doing solubility, you can use that to judge whether something will be solved or not. So you see that if you have, first of all, for something to dissolve in water, it should be polar or it should be charged, okay? If it is charged or polar, then the water molecules, so if it is the water molecules with its partial charge, polarized oxygen and this thing, hydrogen, they can attract and surround it. When water surrounds it, it helps it to dissolve, okay? So for anything to dissolve in water, it should be polar and then it should be charged or charged as well. So the point is, but if the charges are too high for the compound, if the compound has very high charge, then the bond between them is so great that water cannot separate them. In that case, it will not dissolve in water. So the principle is, if you have, let's say, a very small size positive small size is charged, okay, and then small is the charge is small charge, okay, and then you have an anion, okay. If this small size like this is positive, okay, small, let me make it this way so that the principle will be easier to grasp, okay. So if the charge if the bond between them is a little weak, I'll put weak in inverted commas, okay. If the bond between them is a little weak but charge, is weak but charge, and then the sizes of the molecules are big, they are big, they are large. So if you have very large molecules like this, and then their charge is very small, +1, -1, such a compound is most likely going to dissolve in water, okay. Why do I say so? First of all, we said for it to dissolve in water, it should be polar or charged. So if it is charged, that's the charge, okay. So it is, once it is charged, it's likely to dissolve in water. But the charge should be small. So the charge means +1 or -1, or maybe even negative, like partial positive or partial negative, okay. Good. Now, if you have this small charge, if the size, the diameter of the element is very large, okay, if the diameter for each of them is very large, then it means they are reducing the charge density. Okay, they are reducing the charge density. By reducing the charge density, it means the bond between them is going to be relatively weaker, and water can break that bond, so that the bond between water molecules as against this between that are comparable. That is, they are close, so that this can separate in water, so that you have water separated. You have this, and then you say it has dissolved. So you realize, if you look at this principle, as you go down the group 1 here, they are +1, here -1. Okay, so it will look, from what we are saying, it will mean if we have group 1 elements, okay, sodium, potassium, okay, as against these ones, okay, if you go here -1, then it should be what? Soluble. But remember, as you go down, as you go across the period, size reduces. So if it is -1, it's most likely to dissolve. But if it is bigger, then it will make it more likely. So it means that if it is sodium, bromide, sodium, those ones down here which are bigger reduce because as you go down the road, you are adding motion, the size they will become more soluble in water. Okay, so see that down here, so the sodium chloride will dissolve, the bromide will dissolve, and so as you are going. But when it comes to bromide, you have to look at it. Sometimes when the force is so weak too, then it is not becoming possible for water to interact with them. Okay, then it may not be possible for it to dissolve. So the principle is, if it should be charged, and then the diameter should be big. Okay, if the diameters are big, the charge density will be reduced. But still, because they are still charged, they'll be able to dissolve. Okay, so see that group one element, okay, are most likely to give you a soluble compound. Now the negatives. If your negative charge is small, and then your size is big, okay, so the negatives are here, the oxygens and then the halogens, they are here, okay. And then where will they be big? It's when you go down. So when you go down the group, okay, the bigger ones, okay, the bigger molecules with small charge, okay, they are most likely going to be soluble, okay. So see that some will say potassium, sodium, almost all the other things are what? Soluble. They are soluble because they have what? This side, as you go down, the charge is small here, okay, and as you go down, the size is increasing, okay. Good, that is why it is satisfying this. Now, if they meet any other thing, the charge is small, or even the charge is big, because they are so huge, they have reduced the bonding between them, and they will still be able to dissolve. It's that this and that, you have their compounds being soluble, maybe with the exception of some few. Well, now when you come to the cations, which will not, the positive ion which will not dissolve, those with +2, those with +2 and very small, okay. So we are looking at lead, silver, okay, those ones, okay. So see that lead, silver, they are in the +2, okay, and then their size may be also be very small because they are on the other side, on the far part of the table, okay. So that will tell you that they are not going to form soluble kind of what do you call it, compounds, okay. So you see that here the sodium, potassiums are becoming soluble, whilst the lead and then silver are not. Okay. Now if you look at the negatives, the negatives to those which are negative and very large, SO4. Okay. And so for this we have two of them coming together. The total charge on them is what? -2. But we have how many molecules there? So this is a large one, the whole thing on it is -2. It is charged and it is large. Okay? Once it is charged and it's large, then it means it will be more soluble. Okay? It's more soluble because first it should be charged to dissolve in water. And then because it is large, the bond between it and the other cation will be weaker. So water bond between water and this as compared to between it and the other ion may be comparable, and then it will make it more soluble. Okay, so the sulfates, your OH minus, so the minus ones, okay, OH minus are going to be more soluble, okay, unlike when you have very high charge, let's say very high charge and small molecule, very high charge, maybe -3, when it's very small molecule, maybe sulfur -3, then those kinds it's becoming difficult, right, so if the charge is high and the size is also very small, the charge is high, and so the high charges, we are looking at this down the group. Okay, if you go down, it is becoming bigger, but up here. So the sulfide, the oxides, okay, those ones, and then if the compound, the complex they are coming in with are very small, that means we are not having double elements, okay, then that is going to be more insoluble, okay. So the principle, like you said here, they are bigger with small charge, okay. Here, that will make them soluble. Here, they are small with high charge, so it is 2. Here they are small with high charge, so it will be less soluble. Okay, so just to make it very simple, if you have bigger molecules with smaller charge as positives, okay, then they will be able to dissolve because they are bigger, so the density charge on it is reduced, but it is still charged, so it will be able to dissolve in water. The same thing should happen to this one. It should be bigger, and then the charge should be smaller. Okay, so if you come here, those ones which will be soluble will be the bigger ones. The bigger ones are here, and then the charge should be +1. So potassium, sodium, they are going to be soluble down the road. As you come up, they are becoming smaller, so they will not be soluble. Okay, if you go to the other side, you want to see the soluble ones. Okay, they should be bigger. Bigger means it should be what down the road. Okay, and should be here, closer here. If you go far, it is going to be smaller. Okay, so those bigger and smaller, which one are you going to look at? So bigger charge, so maybe +2. Okay, so smaller charge, let's say -1, or -2, and then the size should be bigger. Okay, big enough. So if you have the sulfates, more, you have added more. So this is sulfur and oxygen. It's a bigger molecule, so that will make it more soluble. Okay, if you go to the those which will not be soluble, then it means it should be smaller and the charge should be higher. Okay, so maybe +2, +3, it should be smaller, the size should be smaller. So imagine silver and then what? Lead. Okay, so these molecules of this compounds containing this may not be soluble. Okay, if you come to -2, it should be maybe -2, and the size should be small. So it should be small means it should be up here. Okay, it should be up and further. Okay, so then you have the insoluble ones also coming here for the negative, very high negative. Okay, right. So what you should remember when it comes to solubility is the sizes. Bigger sizes with charge will dissolve. Smaller sizes with high charge will not dissolve. Okay, so that is the principle. And remember silver and lead. As you remember, so the silver and lead as not being soluble. As you remember, potassium and sodium being soluble. Okay, you can work around that. There's a greater picture when it comes to solubility. I will discuss that. You have the bigger picture, broader picture. But this to guide you. Yeah, it's not always the way, but it's to guide you as to predict which one is soluble. Now let's look at hybridization. Now hybridization. So when you say hybrid, simply means mixed. Okay, so you have part of another and then another coming together, hybrid. Okay, so in animals, if you have different races coming together, you may have or different species coming together, you may have a hybrid. Okay, so that's mixing to simple mix. Okay, now we have already talked about the orbits. Okay, like we said, if this is the atom with the nucleus, okay, we have the shells with the principal quantum numbers about K, L, N, G. Okay, these are the principal quantum numbers. Of course, we said they have